Hello, lovely people. I can see Fatima and Aisha, you've been having a lovely chat in the comments. I'm just going to do the usual waiting 60 seconds or so, maybe 2 minutes for everybody to show up, and then we can get started. Did I get my Nando's? Is that addressed to me? No, I did not. Did not get my Nando's. I did get my biscuits, although they were kind of gross, which is really, really sad. Hi, Wad. Fatima, I wanted to say sorry. I saw your question at the end of the last one, but I'd already pressed end stream and I couldn't come back. So I'm really sorry about that. Hopefully, if the next one has a similar topic, you can sort of ask something similar again. Hello, Fatima. How's everyone doing? Has everyone had a nice week-ish? Hi, Abiaz. I think I'm pronouncing that right. From which country am I? This one, England, London. I'm from London. What time is it there? It is 6:30, the start time of the web class. And we're going to give it another sort of... Oh, all right, Fatima. Well, hopefully today I won't mess up the ending. Yes, so my lovely colleague has just dropped in the presentation. So feel free to open that, print it, do whatever you want. I'm going to be starting in like a second. So if you haven't got your cup of tea, it's too late. Oh, Aisha, I'm glad that it helped. It's a bit of a tricky one, but I was reading your conversation with Fatima and I know you did a bit of maths, so you might have been all right. You've got green tea, yay! Okay, good. We're all set for tea. That means I'm gonna get started with all of this sort of housekeeping-y stuff. Just give me a second to share the presentation with you. I'm sorry that your tea tastes nasty, Fatima. Leonide says, any sites you recommend for general papers? So if you're looking for exam papers that have already existed, Save My Exams is pretty good. If you're looking for new questions, then SnapRevise is good. We sort of come up with exam questions. So yeah, Save My Exams, Maths and Physics Tutor, or it could be Physics and Maths Tutor, I don't remember which way around it is. They all have sort of like compilations of exam questions. Okay, I'm gonna get started. I feel like you guys have met me before, so I maybe don't need to introduce myself, but I'm going to do it anyway, just in case there's anybody new hanging around. I'm Georgia, head of chemistry at SnapRevise, so this YouTube channel and content and website. I thought I was going to sneeze, but it didn't happen. It's one of those. It's been sneaking up on me. Right. Master's degree in chemistry-ish. It was natural sciences, and I specialized in chemistry. And I've been teaching for like 6 years now. So lots and lots of experience of the kind of problems you guys end up facing. Recap. So everybody who's heard these recaps before can just like zone out right now because they're the same every time. So the what are these web classes thing, you know what it is. If you've been here before, if you haven't, it's a recap with key points. It's not every single detail that you'll ever need to know. You need to take responsibility for your details, for the small memorizey bits, but I'm here to help you understand sort of like overarching concepts and answer exam questions. And this is sort of like our taster. So this is free, but it costs money to make these. So eventually it will be part of our SnapRevise 2.0 package. And that launches on October the 16th, which I'll tell you more about at the end, you know, after you're exhausted from all of the amazing learning. Yes, so, but there will be some free ones, but most of them will be part of the package. As we have done in previous weeks, one person is going to get a free account. If you tag us in your Instagram story and share a picture of the web class, do a little bit of that, then you might win a free account. And at the end, everybody will get a nice coupon code. I really feel like I'm going to sneeze. It's going to happen when I'm like in the middle of something complicated. I know it's That's how everything works. Okay, cool. We're ready to talk about what we're actually doing. So this is about equilibrium. It's the year 13 equilibrium stuff, not the year 12 equilibrium stuff. We're going to be looking at, we're sort of going to be recapping the equilibrium constant Kc, and then we're going to be looking at homogeneous and heterogeneous equilibrium, and then we're going to be looking at the pressure equilibrium constant and partial pressures and how to do calculations with those. So we're not going to be looking at Le Chatelier's principle applied to these things. So that's like if the temperature changes or if the pressure changes, because there's just not time to squeeze it in, but we will have another session on that later. And we're not going to be covering experiments for determining equilibrium at all. So I'm going to now sort of show you guys the spec points. Aisha says, uh-oh, is that about the tea or is that about something I've just said? Because gross green tea is definitely an uh-oh. Okay, so we're covering AQA, EdXL, OCR. These are the spec points. As I say every time, please, please, please keep up with your own spec points. Have a look, tick them off as you learn things, tick them off as you revise things, tick them off as you do exam questions on things. Take responsibility for making sure you know everything, because I've heard it like again and again from students like, oh, my teacher didn't properly cover this, or I don't remember doing this. And it is your responsibility, lovely people. You are old enough now. Cool, and this is the OCR ones. I'm not gonna hover on it for too long. This, yes, Aisha. We've got OCR. So it's OCR, EdXL, and AQA. Sorry, mind blank just there. All right, let's talk about the things that we should know from year 12 and / from GCSE that's gonna help us do today. Can someone tell me, give me like a really good comprehensive definition of dynamic equilibrium? So like we're talking about equilibrium reactions here. What is a dynamic equilibrium? Okay, cool. Leonide's already in there. So Leonide says the phase dynamic equilibrium means that the molecules of, or ions of reactants and products are continuously reacting, reactions are being continuously changed into products and vice versa. Okay, so that's a lot in there. It's not quite comprehensive enough. It talks a little bit too much about things being changed back and forth. We've got Aisha says that the forwards reaction is the same rate as the backward reaction. So that's getting us closer. That's getting us a lot closer. Aisha says the same thing, closer. Charlie, yeah, we're closer. So the one thing that sort of Leonide has sort of got, but not said in a concise way, is that it's a reversible reaction. So that's the first thing you've got to say. Yes, thank you, Deca or Dika, the system is closed. So you also have to say it's a closed system. So I'm going to put in a reversible reaction. So you can't set up an equilibrium if the reaction can't go backwards, right? That doesn't work. So you have to say in a reversible reaction, and then we can go ahead and say the thing that you guys were getting completely right. The rate of the forward reaction is equal to the rate of the backwards reaction. This must be in a closed system. That doesn't look like it says closed. Okay, all right, I'll just rewrite closed. Yeah, I say it every time. Please tell me if you can't read my writing. It's actually quite difficult to make it look legible when you're writing on a screen. So help me out if it is illegible. So I have mentioned a closed system. Deca mentioned a closed system. What do we mean by a closed system? Why is that so important for setting up a dynamic equilibrium? Yeah, Fatima, you're totally right about equilibrium shifting to opposed change. That's our Le Chatelier's principle that we're not covering today, but you're totally right. So Charlie says no gases can escape. Yeah, that's true. So why is that important? Why do you want nothing to be able to escape? What will happen if something escapes? What changes? Yeah, so MK says concentration remains the same. And yeah, Charlie says so that the backward reaction can occur. Yeah, so we're right. So essentially, if you like take something out of the reaction, it's no longer going to have the same equilibrium. So it's not, you're not setting up a dynamic equilibrium. So it's got to be a closed system. Yeah, and things could get in and then that changes the reaction. So it's just like the whole thing breaks down if it's not a closed system. Okay, so the next thing I want to have a nice definition for, which you guys should probably know from GCSE, is what is a catalyst? Give me the nice textbook definition for catalyst. So Aisha says an enzyme. Okay, so catalysts aren't necessarily enzymes, although enzymes are catalysts. They're biological catalysts. Leonide says subs that increase the rate of reaction but remains chemically unchanged itself at the end of the reaction. I like that definition, Leonide, because often people say chemically unchanged full stop, which is untrue because obviously it has to change during the reaction. It's just it goes back to its old self at the end. So Abyaz, you're kind of almost right. So it does kind of react within the reaction. It's just that it reforms at the end a lot of the time. So I'm going to, yes, Fatima, it does. It gets regenerated. So I'm going to say something that increases the rate. I should probably have put a chemical that increases the rate of reaction, but I'll let you correct me. The rate of reaction, but does not undergo permanent change. And I'm seeing Sheba writing a really good definition there. A substance that lowers the activation energy by providing an alternative pathway. That is a beautiful definition. Yes, so that is another way you can define a catalyst by looking at how much activation enthalpy is required for a reaction to take place without it, and how it's the difference in reactivity gives you a lower activation enthalpy. So well done, Sheba. That's also a wicked one. Right, nice and easy. What is our symbol for equilibrium? And this might actually be quite difficult to do in the comments. So yes, thank you, Aisha. So 2 half arrows. Yes, and it suggests that it's a reversible reaction. Yes, so this is the important bit. You must do this arrow for equilibrium, or it's so not a single-headed arrow, Hugo. It can't be single-headed because that means that it's not a reversible reaction. So you've got to have both. And how do we denote concentration? Concentration of a reactant or product? Square brackets. Yeah, lovely. You thought it was biology. Sorry, biology is Mondays and Wednesdays. Oh, look at that. Riley Sersha has managed to actually find one. Yes, okay. So we're good to move forward to the actual content. So we're going to be Google. Yes, Riley, Google is fabulous in that way, isn't it? Okay, so I am going to keep drawing in the equilibrium symbols because, unfortunately, the font we use does not have the equilibrium symbol. So every time there's like a little gap, I'm going to have to draw it in. But it's a good reminder of what kind of symbol you should be using. But yes, Shahid and Riley, it is good that the equilibrium symbol exists in whatever font that YouTube uses. Cool. All right, someone help me out. So Kc is the equilibrium constant for concentration. And it's the way we describe things numerically, quantitatively. It describes the position of the equilibrium. So does anybody remember, how do we go from, so just in case you're a bit confused about like little a, big A. So the little a's are representing our moles, and the big A is sort of like a substance. In the rate equation. So Hajar, first of all, this isn't a rate equation, this is an equilibrium equation, which is different. And no, you don't put catalysts in either, because a catalyst should not change the position of an equilibrium. It should just increase the rate. And it, yes. So can somebody sort of using this AA plus BB system, could you tell me what the equation is? And Aisha has sort of done it while I'm, yeah, so somebody, both Charlie and Aisha, saying concentration of reactants in small letters in the power of the molecule. So Aisha says products over reactants. Yep, so we've definitely got products on the top, and we're going to use our square brackets. And the small letters are the powers, and Aisha's totally right about that. Yeah. So this is Kc, the equilibrium constant for concentration. So the next thing I want to do is look at an actual example. So this is, oh, lovely. Yes, Hugo, that is totally correct. It's quite difficult to type it in. I don't know if you can put in pictures in the comments. I don't think you can. It would be useful though, wouldn't it, if we could take pictures of what you guys have drawn and shove it in, but never mind. So can somebody, lovely, tell me what Kc will be, the equilibrium constant will be for this reaction? So our sulfate reaction with oxygen. And apologies for how long all of this is going to take you guys to write in the comments. Oh, yeah. So I will let you off for the power, Charlie, because it's going to be long. Yes. So we've got SO3 squared over SO2 squared O2. Don't have square brackets. Are you on an iPad or something? You should have square brackets somewhere. But yes, well done, everybody. So the next thing I want to talk about is, of course, units, because nothing makes sense unless you have units. So how do we usually find the units of something that has lots of terms involved? What do we usually do with our equation? So Sheba says cancel out, and you're right, but like go into more detail for me. What do we mean? What do we mean cancel out? Cancel what out? Expand what? Anybody? Units? Yeah. So Ahmed's sort of explaining it the best. Yes, so you want to put all of the units in the actual equation. So that's what I was missing. So as you guys have said, so the units for SO3 is going to be moles per dm cubed, and it's going to be squared still. And this is going to be moles per dm cubed squared. And for oxygen, it's just going to be moles per dm cubed. And you're right. You can cancel that one and cancel that one, because moles per dm cubed squared, moles per dm cubed squared will cancel. So all we have left for Kc's units in this case is 1 over moles per dm cubed, or we could put it in brackets and put it to the -1. And yeah, Abiaz has expanded the brackets for us and has rightly said moles to the -1 dm cubed. Cool. So the important thing about learning about Kc and Kp is that you actually know what it's talking about. Like, how are we analyzing? I thought it was spelled mole. So mole is like the shortened version. It's a bit like writing cm instead of centimeters, except that the word mole is already really short, so it just doesn't look that different. That was to MK Ulsterboy, by the way. So tell me what it means for Kc or Kp or any equilibrium constant to equal 1. So why does it equal 1? What, I mean, not why, like what does that mean for the equilibrium? Yeah, so so Emily, what does it mean for them to be exactly, the equilibrium to be exactly in the middle of what? And Ahmed sort of said, yeah. And Sheba says, I'll come back to Sheba's because you're jumping ahead, but well done. But yes, so if the equilibrium constant is equal to 1, then that means that the equilibrium is exactly halfway between products and reactants. So we can kind of see that that must be true, right? Because if we had the same concentration of C, D, and A, B in the same moles, then you would have the same number on the top and the same number on the bottom, and anything divided by itself is 1. So that totally makes sense. And then I'm going to look back up at Sheba's comment. So Sheba has said that if K is smaller than 1, then the mixture mainly has a reactant. And if K is larger than 1, then the mixture mainly has products, which is true, but we say it a little bit differently. So when we're talking about equilibrium, we talk about the equilibrium being shifted towards something. So if K is smaller than 1, then the equilibrium is either shifted towards the reactant or shifted to the left, because we're talking about here. So you can either say to the left or towards the reactant. I mean, I think it makes more sense if you're talking about to the reactant because it's more descriptive, but you can say either. So equilibrium is shifted. Oops. Towards reactant / the left. And Leonide has said equal than, yeah, Leonide has got a really beautiful definition there. Everybody have a look at Leonide's. While I write if K is bigger than 1, so if K is bigger than 1, then the equilibrium is shifted towards the product. Oops. Why will it not let me write here? Oh, there we go. / the right. What do I mean by shifted? So I'm going to redraw the equilibrium sign. So this is quite useful. By shifted, I mean that if you imagine equilibrium as a position, is that AQA? Because I've never seen it before. Is what AQA? The term shifted? Aisha? So this is definitely on all of the syllabuses. You might have, so you will have done equilibrium in year 12, which means that you might have done like a sort of less in-depth version of it, and your teacher may be waiting to do more depth this year. So that might be but yes, but everybody needs to know what K actually represents. There's no point really knowing what KC is if you don't know what it means, right? So what I was about to do is draw the arrows. So if K is smaller than 1, then you could draw the equilibrium arrows like this, so that you can sort of the one on the top is larger to show that it's shifting towards the reactant rather than the product. But yeah, Charlie, go ahead and check the specification. Have you done it? So like, it will be useful to know this, people. It's there's no point knowing what a constant is if you don't actually know what the constant represents, right? And it's also kind of logical, right? Because if the products are larger, think about it. If C and D are a larger number than A and B, then KC will be bigger than 1, because it's like doing 10 divided by 2. You still got a positive number, which means that they'll be shifted towards the products. And if on the bottom you've got a larger number than the top, you end up with a fraction, which means that you've got less than 1, so it's shifted to the reactant. So it's it's just logic. You may not have been. So Fashima says, so K can be a really big number, like 10,000, Or is the range of KC really small, just so I know if my answer is completely wrong when practicing questions? It can be, the range is quite big. It really depends on how forward the reaction is. It's not going to be like a billion, just because there's always going to be like a tiny bit of reactant. But keep in mind that the reactant could be like 0.0001, and if you're dividing by that, then the number is going to be massive. So it really can be quite different. Okay, I'm going to move on. We all seem to just be having a bit of a complaint about our teachers. I'm sorry if you don't like your teacher. I think that happens to everybody at school or college. At least once you have a few teachers probably that you don't like very much. Hopefully, Ulster boy, I can help you with that. So hopefully we're all good so far. We've just got, I didn't know that a letter was a number. Do you mean that you didn't know that they had replaced? Explain. So when you guys say like things that had confused you, it's really helpful if you sort of assume I don't know what you're talking about at all and give me like lots of detail, because I don't know what you mean by I didn't know a letter wasn't a number. That's confusing to read. Thank you guys. I'm glad that you're finding my lessons useful. But I'm gonna move on, and we're going to talk about homogeneous and heterogeneous equilibrium constants. And you should have seen even if you haven't seen the words homogeneous and heterogeneous before, then you should recognize the beginnings of the words, right? So homo means same and hetero means different. That comes up loads, like homosexual, heterosexual. You will have seen those words at some point. So it's easy to remember. So what do you think I might mean by homogeneous equilibrium? What could be the same? Yeah, Fatima. Yeah, exactly. Saba. So when you've got all species in the, and by species I mean like all of the reactions, all of the products in the same state or phase, then that is a homogeneous equilibrium. So it could be like a gas and a gas, or a liquid and a liquid, aqueous and aqueous, whatever it is. Although it can't really be a liquid and a liquid, because if you have a liquid and a liquid, it's technically aqueous, but yes. So have species in the same state / phase, e.g. gas and gas. All right. Could I go over that? I'm sorry, we're not, Hajar, we're not going to do that in this web class because there's just not enough time, but we'll do one like that later on. So don't worry, we'll cover it at some point, but not today. So if that's a homogeneous equilibrium, it's kind of an easy one. What is a heterogeneous equilibrium? If homogeneous is that they've got the same state. Yeah, cool. Different states, the opposite, exactly. So have heterogeneous equilibriums, have species in a different state or phase, e.g. gas and solid. Cool. No, hetero means different. So like heterosexual, you are attracted to a gender that is different from yours, different. So what we're going to do is talk about the fact that homogeneous equilibriums are basically all of the ones that you've seen so far, because it gets a little bit complicated when you're talking about different phases. So again, I'm going to have to draw in my little arrows for both of these. And if somebody lovely could write down what the KC for this is, that would be wonderful. Do you have to draw the arrows differently? No, if they look different, it's because my drawing sucks. Sorry about that. Yes, they do. June, it's really hard to draw these arrows on a screen. It never looks right. Just imagine that it looks not rubbish. Use your imaginations. K is Kelvin. That's true, but Kc is the equilibrium constant. Yeah, so we've got Hi, thank you, Charlie, not Charlie, but yes, Charlie and Decca and Fatima. Hi squared, and then on the bottom, we've got H2 and I2. Yeah, perfect. Okay. So what we're going to talk about with heterogeneous equilibrium is essentially that it's a little bit different, because if you think about a solid, if you have like something solid in a liquid, the likelihood is that it's going to be in excess. There's going to be like a lot of it compared to the amount that's in the solution. And it's the same with liquid. If you've got water in a reaction, it's probably in excess. There's not going to be like a splash. It's going to be way more, which means that it does not, adding a bit doesn't change the equilibrium. Taking away a bit doesn't change the equilibrium. So we tend not to include them at all. So when we're looking at equilibrium equations for something where you've got a solid and a liquid reacting, and all you've got in the end is something aqueous, then literally we just include that term. So in this case, Kc is just that. And we don't talk about P4O10, and we don't talk about water because they are just such in excess. So I'm going to put a little note on the bottom. Solids and liquids are often in excess. Don't worry, you will be told if they are in excess or not, unless it's water, in which case you can kind of just assume it is. What if the end product was still solid, liquid, and gas? Is it still hetero? So as long as there's more than one state at all, that's heterogeneous. If they have to everything has to be the same for it to be homogeneous. How do you know if it's in excess? They will tell you. So like, let's say, I mean, like there are ones that you kind of have to remember. So often water will be in excess. Like think about anything aqueous. You've got like tiny bits of like, let's say you dissolve salt in water and you're reacting that. You've got NaCl and you've only got a few of those particles compared to like the massive amount of water that it's dissolving in. Otherwise it wouldn't dissolve. So anything with water and the product that ends up aqueous, it's going to be in excess. If it's not water, they will tell you. You don't have to sort of like figure out if, but like what you do need to remember is that solid and liquids are often in excess. You might be asked to explain why heterogeneous equilibriums don't include them, and then you would say because they are in excess. So that's basically it. So we don't include them in Kc. Can I give you different examples? Different examples of what? Did you send that before I gave you examples? Or do you still want examples of heterogeneous? We will, I believe the exam question that comes up. So the units would be moles per dm cubed to the power of 4, right? So you're always, for units, you're always shoving in the units for the concentration and then just calculating it for Kc. Aisha, I think that the exam question is an example. If it's not, I will find you another example. But we're going to move on to the how are you feeling about this, and then go ahead and do the exam question if you're feeling okay. So rules for how are you feeling is if it is bad, if you're feeling bad, then you have to tell me why, or I can't help you. So please tell me why. And if you're feeling good, then just go ahead and send me an emoji. Ulster boy, I don't know what that means. Does that mean you feel okay, but you don't like equilibriums? I'm glad, Ahmed. I'm glad that you can get some practice in. Ulster boy, you have to tell me what's confusing, or tell me which slide to re-explain, or what is Famida. You gotta tell me, or I can't help. I can't just sort of like go back and re-explain everything. I have to, pick something, because you might get one thing but not the other. And I don't want to waste anybody's time. So please tell me what is confusing. Ahmed says, I feel in chemistry applying knowledge is hard. Yeah, I mean, like, that's the same for life. Anything you learn in life, any subject, whether it's like a school subject or just like a life lesson, that's like half the battle. The other half the battle is actually getting your brain to apply it to new situations. It is a tricky thing. If nobody's going to tell me why are solids avoided? So they're not avoided. They're not avoided. So if we have a heterogeneous reaction that's set up, it's an equilibrium reaction. If you have a really, really high concentration of something, like let's say in this reaction, you've got like, let's say we've got like 10,000 moles per dm cubed of this solid. And then in our product, we've only got 1 mole per dm cubed. And that's often what happens with solids because they're so dense, right? Think about the way solids exist. You've got lots of particles lined up all in a row. And with something that's aqueous, you've got little bits of it floating around in liquid. So if you've got like 10,000 moles per dm cubed, as opposed to 1 mole per dm cubed, changing the concentration of that massive solid does nothing to the equilibrium. It does absolutely nothing. Adding another 10, adding another 100, adding another 1,000 does nothing to the equilibrium. So adding it to our equation, the Kc, is pointless because if any change in Kc is based on the concentrations, right? And if something's concentration doesn't matter, then we shouldn't put it in. What's it called when you go from a gas to a solid? That's a really good question. Solid to gas is sublimation, and I've completely forgotten. Somebody Google that for me because I should probably know that. Anyone want to Google? No, sublimation is the other way around. Deposition. Is it, RN? Thank you, RN. Yeah, guys, sublimation is the other way around. Solid to gas is sublimation. Ah, wicked, Famida. I'm so glad. Okay. You're welcome. Let's go ahead and do these exam questions because they tend to be the tricky bit. So I'm going to say what I usually say with exam questions, which is don't write it in the comments. Don't write your answer in the comments until I say, but nobody ever listens to me. But if you could wait for me to say, then that really gives other people the chance to do it themselves. So I would really appreciate it if you don't answer the question before I say answer the question. Yeah. So you want to be like working out on paper or wherever you're doing your working out, but don't shove it in the comments yet. Or like write it and then don't press enter. And also, if you're suggesting that everybody does it before we talk about it, this is very mean. Literally nobody's ever listened to me. I don't know why it's so hard for people not to press enter. Anyway, sorry. Okay, we're going to get on with it because I'm just rambling about the difficulties of getting the youth to listen to me, who is also a youth, but less youthful because my face has more wrinkles now. Okay, Kc. So that's the easy bit, right? Writing Kc for this expression. I'm gonna read the question first, though. Okay, a chemist carries out an investigation on an equilibrium system shown. So this is carbon monoxide reacting with nitroxide, and that creates carbon dioxide and N2. The chemist mixes 0.46 moles of CO with 0.45 moles of NO. The mixture is left to reach equilibrium at a constant temperature. The student analyzes the equilibrium mixture and finds that 0.25 moles of NO remain. The total volume of the equilibrium mixture is 1 dm cubed. Write Kc. So this is your opportunity to actually write in Kc. So what is Kc? So we practiced this quite a bit, so you guys should be okay. Thank you, Aaron. Thank you, Fatima. Thank you, Charlie. Yes, we are all right. So Kc is equal to CO2 squared N2, because those are our products. And then our reactants go, and that's also squared, and NO is squared. Oh, that is not a square bracket. Wicked. Okay. So Then the next question is what are the units of this equilibrium constant? So if we sort of just have a look, if we know we're gonna be shoving in dm cubed for moles per dm cubed, sorry, for CO2, N2, CO, NO, and we know that some of them are going to be squared, but a lot of them are going to cancel. So which two are going to cancel, or sort of like what are we going to be left with once we've cancelled them out? Feel free to shove things in. So we're getting a lot of right answers, I believe. Yes. Yeah. I mean, Aisha, I think yours was just written in dodgily. I think you've got it. So let's, Charlie, yours is slightly dodgy. I'm going to go through it over here because there's not enough room there. So we've got moles per dm cubed squared, moles per dm cubed over, oopsie, moles per dm cubed squared again, moles per dm cubed squared. Okay, so these ones cancel. So we can get rid of, Amir, I'll get back to you. We can get rid of these two here. So now all we have left is moles per dm cubed over moles per dm cubed squared. And then, so the top one will cancel and the bottom one will get rid of its cubed. So we'll just have 1 over moles per dm cubed, which means that if we expand this out, we should have moles to the power of -1 and then dm cubed without the -1. So well done, everybody who got that. And I will shove this in where it's supposed to go. So that is moles to the -1 per dm cubed. Okay, so now we've got the actual calculation where we have to shove in all of our figures, which is fine because that's nice and easy, bar 1. Before I do it though, somebody asked me if I had any general advice. General advice at A-levels is always be doing exam questions. Do not wait till the end of the year because you will not have learnt any of the syllabus in the right sort of angle. You want to always be answering all of your questions, learning all of your things the way the examiners want you to know. And unfortunately, the textbooks don't necessarily make it clear which specific things you're supposed to know. So yes, always exam questions. Right, so determining the Kc. So what we need to know essentially is the concentration the number of moles for everything. So so the reason that we're doing, we're not going to bother with moles per dm cubed is because the equilibrium mixture is 1 dm cubed, right? Which means that it's already per dm cubed. So I'm just going to ignore that. I'm going to ignore the dm cubed, and I'm just going to figure out my number of moles. So the first one I'm going to look at is CO, and the number of moles of CO is not, okay, somebody help me out. How are we going to figure out the number of moles of carbon monoxide at equilibrium, not when it's put in? How do we figure out what it is once the equilibrium has been reached? Try refreshing the page. And face is a little bit laggy too. Yeah, try to refresh the page. Sometimes that helps. Work out the change in moles. Yeah, so both Ahmed and Decca are right. Decca, you want to write in the comments how you managed to get to 0.26? So Famida, that's not actually the final answer. Substitute the numbers in the expression. Voice is not synced with the face cam. Okay, is everybody else having trouble with a lag? It's 42. Okay, so we've got 0.26. Compare the moles to start with the moles equilibrium. Yes, that is totally right, Fatima. So we're going to be comparing them. So we've got lots of yes and no's. And I can't remember what question I asked, whether it was, is there a lag? or kind of. So there is a lag. I'm not really sure what I can do about that. If it gets so bad that you can't understand what's going on, then I'll have to have a think about what to do. But for now, as long as it's okay, is it sort of like manageable? It's not bad. Make the face bigger. I can't make the face bigger. But also you don't need to see my face. You need to see the screen. It's bad. Manageable. We're getting lots of different responses. That's okay, Aaron. I'm gonna move on to how to get. It's not 2.6. It's 0.26. But yes. So what we need to do to figure out the concentration of CO at Kc is we need to figure out first, because we've only been given the equilibrium number of moles for NO, not for CO. So we need to figure out how much of the NO has been used up, right? So we know that we put in 0.45 and we know that at equilibrium it's 0.25. So to figure out, maybe I should have just done NO first, right? So to figure out how much has been used up, what we're going to do is 0.45 minus 0.25, which just gives us 0.2, right? So we know that 0.2, we know that 0.2 moles of NO have been used. And we also know that the same amount of moles of NO reacts with carbon monoxide, right? Because they both got 2 moles. So that means if 0.2 moles of NO have been used up, then 0.2 moles of CO also have to have been used up. So what I'm going to do is take the initial concentration of carbon monoxide, which is 0.46, and I'm going to minus 0.2, which is how much has been used up, and that gives us 0.26. Does that make sense, everybody? Can I see some emoji feedback? Am I good to carry on? Yeah, Aaron gets it. Yes, Fatima, it is double. It's double the change. Thank you, colleague, for letting me know. It's all fine. Don't I use rice? I do not use rice. I do not know what rice is. If it's something to do with initial concentrations, I am using that. I'm just not drawing a table. Thank you, everybody, for the emoji feedback. Honestly, I think it's like as soon as it gets past 7, my brain starts going, what do you want words? You can't have them. But yes, so everybody's good. So we've got the number of moles of carbon monoxide. So the next thing I'm going to do is the number of moles of carbon dioxide. So if we know that we've had 0.26, 0.2 used up, then that means what? How many moles of carbon dioxide will we have if 0.2 moles have been used up in the reaction? Not 0.26. Remember, this time we're looking at the products, not the reactants. Yeah, Decca's right. So it's 0.2. So if the reactants if we've reacted 0.2, that means that 0.2 must then be in the products, right? So CO2 is 0.2 moles. Aisha says rice is ratio initial change equilibrium. I don't use that acronym. I'm sure it's useful for some people. I've never seen it before. Different teachers do things in different ways. I prefer to sort of go logically through first principles, so that no matter what you're looking at, you sort of have a sense of it. But I'm sure that is also useful. I might have a look at using it later on, but I can't use it right now because I've never seen it before. Okay, so we're going to move on to NO, which we've already been given the number of moles of at equilibrium, so we can just nicely just write it down because it says it up here. It says it right here. Okay, And then last of all, we've got N2, which is just not letting me write at the bottom of the screen. And Fatima has beautifully said that it's 0.1, which is correct. So is everybody okay with how we got all of those moles? Because if we are, we can just go ahead and shove it into the equation. Yeah, we seem happy. Okay, so now we can just shove everything in. And we have our equation here, so we don't even have to think about it. We just need to literally just shove it in. So 0.2 squared times 0.1 over 0.26 squared times 0.25 squared. Aluna, what is confusing? Try to explain what's confusing, because it's really hard for me to help if I don't know what bit you sort of got lost at. And so if you shove that in your calculator, you will get something long like 0.94675 and so on. So I'm just going to round that to 0.95, and we've got our units. And please, please, please put in your units or you will lose marks for no reason. Yes. So Aluna, please tell me what is confusing. Yes, Famida, it is 0.946, but we kind of want to round. We're going to round to 2 decimal places because that tends to be a standard unless it says otherwise. Yeah, wicked. Hajar, you're right as well. So Aluna, I'm going to move on. So the Insta is SnapRevise. It's literally just SnapRevise, which means that the equilibrium, yay! Okay, so Dec has already answered the question. So the question is, what does your value of Kc suggest about the position of the equilibrium in this experiment? And we're subtracting the number of moles used. Okay, I'm going to finish my sentence and then Aluna come back to you. So Deca is totally right. So we learned earlier that if Kc is less than 1, that means the equilibrium is shifted to the left towards the reactants. Okay, so Aluna says we're subtracting the number of moles used. Okay, so I think you mean that the confusing part is like how we're managing to get the number of moles at equilibrium. So essentially, I'm going to sort of write it below. So the only knowledge we have is we have the initial number of moles for CO, we have the initial number of moles for NO, and we have the equilibrium number of moles for NO. So that is, colleague, could you possibly put in the Insta for SnapRevise in the comments? That would be great. So we only know so far that at equilibrium, there's 0.25 moles of NO. So because we know we started with 0.45, to figure out how much has been used up, we take one away from the other, which gives us 0.2. So if we have 0.2, then we also know that the products, if 0.2 was used up, then that means that we have 0.2 moles of the products, right? Because that's what it means to use up. It means that the reactant has become the product. So we know that we have 0.2 of CO2, and we know that we have 0.46, which is the original of CO, minus 0.2, which is how much has been used of the CO. Does that make sense? So Ahmed says for Kc, you put in concentration. So in this case, you'd have everything. You have everything in this over volume. So Kc is concentration. The only reason that we're going for number of moles is because it says the total volume of the mixture is 1 dm cubed, which means that by default, everything is per dm cubed. So we've got 0.46 per 1 dm cubed, which is exactly what moles per dm cubed means. No, you cannot have my personal Insta. It is, you've said it yourself, personal is the operative word, personal. That would be weird. No, you cannot. Okay, people, I'm going to move forwards. It's not a silly, it's not a silly thing to ask. This is quite a tough question. It sort of, you need to do a lot of thinking for it to work out. You need to do a lot of reading. So that's why I read the question quite carefully at the beginning. And I'm going to move forwards because it is already almost 7:30. I literally just cannot keep time. So we're simply removing the number of moles used up. Yes, Luna, that's exactly right. KP time, yes. Pressure instead of concentration. So we've been looking at a lot of concentration equilibrium, so stuff that happens in an aqueous mixture, so something with water. And we haven't talked about how we figure out equilibrium if we have gases, right? Which is important because not everything happens in aqueous form. So we do this by working out partial pressures and shoving them in the equilibrium equation instead of concentration. And it's almost exactly the same, just with partial pressures. So can someone tell me what a partial pressure is? Anybody? No idea? Anybody else? But thank you, Logan, for replying anyway. So Aisha says the mole fraction time over total, mole fraction time total pressure? Do you mean over? Pressure of the chemical over the total pressure. Yes, mole fraction. Yes, so you're all getting it, but we want to like avoid using the word mole fraction until we've defined mole fraction. We want to use simple terms. So partial pressure is basically, let's say you have a reaction chamber and you've got all of the reactants floating around because they're gases. If you're looking at a specific reactant or a specific product, the partial pressure is how much that reactant or product contributes to the total pressure. So the pressure of the reactant over the total. So I'm going to write partial pressure is the contribution of each reactant or product to the total pressure. And then I'm going to draw my weird equilibrium sign that everybody thinks is so dodgy. That's worse than usual. So I'm going to rub it out. Yes, there is my beautiful equilibrium sign. So partial pressure, we write it like this. We write P subscript whatever the thing is. So if it was CO2, it would be P subscript CO2. If it was water, it would be P subscript H2O. But right now we're using A's and B's and C's and D's. So I'm going to write KP, and it is exactly the same as the way you do the concentration. So instead of doing square brackets, because we're not in concentration anymore, we're in pressure, we've got just normal brackets. So it's the partial pressure of C to the power of C. And somebody finish me off. What is the rest of KP? And all of those people talking about the mole fractions, you are fabulous. We're getting there in just a second. And Aluna, yeah, partial pressures don't come up very often in chemistry until this point. So yes, it usually only comes up for like respiration stuff in biology. Yep, it says P brackets instead of square brackets. You're totally right. But what I want is the rest of the KP expression. So I've sort of given you partial pressure of C to the power of C. So remember that C is in our products. Same equation as KC. Aisha, that is lazy. What I mean is somebody write it in. We also have to put P before. We don't have to put P before because P is in the term for partial pressure over here, which you can see, but we'll talk about that in a second. Saba is too tired. Thank you, Karina. Look at you. And thank you, RN. Yes, look at you lovely people who are not too lazy to write it in. Yes. So it's literally reactants over products again. PA, PB, power of B. Which one is lowercase, which one is uppercase? I think you can see now. I assume that's why you retracted your question, RN. Okay, so the next thing we're going to talk about is how to work out partial pressure. And this is something Famida was sort of talking about. So big P, or not big P, P on its own, P without a subscript is total pressure. So that's like if you're in a reaction chamber, that's the whole pressure of the whole thing. So like in the air, the total pressure is 1 atmosphere, right? And then that includes oxygen and carbon dioxide and nitrogen, and then all of those little itty bitty ones. So total pressure is just like the general pressure. And to work out the partial pressure, we have to times it by something called the mole fraction, which you guys have all been mentioning because you're fabulous. So the mole fraction, does somebody want to give me the equation for mole fraction, even though lots of you have already done it? Tell me again, what is mole fraction? What's XA? Mole fraction. Just what I've written. Can you use this to work out the partial pressure of oxygen when it binds to hemoglobin? No, because that has to be kind of like, it has to have more assumptions involved, because anything in a biological system has so many factors involved. And when you're talking about partial pressure in chemistry, you've got a very controlled system. Often it's your reaction chamber, you know the exact pressure, you know exactly how much gas you've pumped in, whereas when it's in the human body, it gets kind of fluffy. So you can't do it exactly like this. And somebody, Famida says, no idea. Yes, that is a perfectly legitimate answer. And Aisha says fraction of total moles. Yes. And Aaron says the mole over the total moles. So yes. So if we're talking about A specifically, it's the number of moles of A over the total moles of gas in general. Yeah, thank you, Wad. Perfect. So mole fraction is XA. PA, P subscript, anything is partial pressure. P without anything there is total pressure. Yeah, Melina, that makes sense that you would get graphs, because graphs will tell you what the experimental data is telling you rather than you trying to sort of estimate it like we're doing here. Okay, I'm going to move on. I'm going to move forward, and we're going to actually have a go at calculating KP. And I'm going to move my little face on the screen because I can not see my actual question. Okay, cool, wicked. So calculating KP. So this question is 5 moles of SO2 react with 4 moles of O2 at 300 Kelvin at 4 atm. So atm means atmospheres. When the reaction reaches equilibrium, there are 2 moles of SO2 left. Calculate KP for the reaction. So this is another one, Aluna, where we're going to be having to do some minusing to figure out how much product, how much reaction we have at equilibrium. So I'm going to draw my weird equilibrium sign that you all have made fun of, which makes me so sad. Not really. Oops. Oh no. Where have I gone? Okay. So at equilibrium, I'm going to first work out my moles at equilibrium. So we already know what the number of moles for SO2 is at equilibrium because it says it, but I'm going to get you to make sure you've actually read the question. How many moles of, and why have I done a big M? How many moles of SO2 are there at equilibrium, people? Five, not 5, at equilibrium. Yeah, it's just 2. So 2 moles left at equilibrium, which means there are two moles. That's what it means by 2 moles of SO2 left. So I'm actually really glad I asked that question. So when it reaches equilibrium, there are 2 moles of SO2, which means that we're looking specifically at SO2. So it literally says it. We're going to be minusing next. But not quite yet. So the next thing we want to look at is the number of moles of oxygen. So we know that we started the reaction with 4 moles, right? We started the reaction with 4, so that's where we're going to start writing something. So what do we do next? What do we do with that 4? It is 2.5, Fatima. Why is it 2.5? Why is it 2.5, Logan? Yeah, so you all seem to be doing, so why, but why? But where do we get this 1.5 from, people? It's -3, so the mole ratio is 1.5. Yes, so I'm going to sort of like break it down. Yeah, you're right, because there's a 2-to-1 mole ratio. So you guys seem to be you do it a little bit differently from me, but I'm going to explain it my way. So if we look at the SO2, and we know that we basically want to know how many moles have actually reacted with O2, right? So we know that we've got 2 moles left of SO2, which means that we've had 3 moles of SO2 react, because there were 5, there's 2 left, so 3 of them reacted. But we also know that, so I'm going to write that 3 react. We also know that half the amount of oxygen reacts with SO2, because there's 2 moles here and 1 mole here. So we have to divide 3 by 2, which is 1.5, which gives us 2.5 moles of O2. So the next one we want to work out is how many moles of SO. Oh, that was SO. Oops, have I mixed up my, no, I haven't. Okay, so SO3. So now we want to know how many moles of SO3 there are. Can anyone tell me? So we're getting a 3. Anybody else? Anybody? So everybody's saying 3. Somebody want to put in why? Why are so many people saying 3? Anybody want to explain why there are 3? Same mole ratio of SO2 to SO3, 0 moles initially, change of 3, so that's 3. Yeah, cool. Yes, so we've got lots of different ways of explaining it. So we know that we've got the same ratio of SO2 to SO3, and we know that 3 moles of SO2 reacted, right? Because we've got 2 left and we put 5 in. So therefore, we must have 3 moles of SO3. Okay, so now we're in a really, really good place, because all we have to do is work out our partial pressures, which means that we need our mole fractions. So can somebody tell me what is the total number of moles in the system? Getting some good answers in there. Yeah, so we have 7.5 moles in total. All we have to do is add them all up, right? These are everything that's in the system, so there must be 7.5. So when we're working out our mole fractions, and remember that it's X subscript whatever the thing we're looking for is, we put the number of moles over the total, so 2 over 7.5. And I want some lovely people to list in what these fractions are. Oops. When we're looking at them in our calculator. So what is 2 over 7.5? What is 3 over 7.5? Help me out here. So lots of people are saying, yeah. Cool, we're getting 2.66, which is right. It is 2.6 to 0.26 recurring, and then we've got, yeah, and then we've got a third, so 0.3333, and then we've got 3 over 7.5, which is 0.4. So lovely, everybody's got it. What I'm going to do is just leave it in the fraction for now, because it's more accurate when you've got recurring things to just leave them as their fraction when you shove them in the calculator. So the next thing I'm going to do is actually work out our partial pressures, so we can go ahead and shove them in the equation. So if you remember, the way you work out partial pressure is what? What's the equation? What is the equation for partial pressure? Yeah, you want to times it by the total pressure. Times what by the total pressure? Rn. Yep. So Aisha, we're not quite there yet. That's how we get Kp, the equilibrium constant for pressure. Fatima is right. It's mole fraction times the total pressure. And we've been given the total pressure. The total pressure is 4 atmospheres. So we've got mole fraction for SO2, which is 2 over 7.5, and we're going to times it by 4. And we're going to do the same for SO3. We're going to do 3 over 7.5 times 4. And we're going to do the same for O2. So we're going to do 2.5 over 7.5 times 4. So everybody should have a go at shoving that into their calculator. So that we can have a go. What's the point of temperature? So this was in there when I was going to do some of the Le Chatelier's principle, but I'm not doing that anymore. So ignore that. And we're getting lots of, yeah, so we got Decker's correct for the first one, 0.67-ish. The second one, somebody tell me what it is for the partial pressure for SO3. Yes, Luna, it is. It's a lot of working. 1.6, lovely. Thank you, Farmada. 1.6, and then the last one is 2.5 over 7.5 times 3, which I'm just going to give you. They're not worth 10 marks, I'm afraid. They're just really long and annoying. But the more you do them, the faster they get, to be fair. Okay, so now we can finally just shove them in the KP expression, which you guys should already know because we've gone over it lots and lots of times. So it is products over reactant as always. So we've got 1.6 and then there's 2 moles of it. So we square it. And then we've got the rest. There's only 1 mole of oxygen, so we're not going to square it. And then we've got the PSO2, which we are going to square because there's two moles of them. And if lovely people could just shove that whole thing in their calculator so I can see you guys. Yes, finally is right, Aluna. Finally is right. Anybody want to give me, what did you guys get? Yeah, 1.75. Lovely. Your so we've got. So remember that I should remember that the units are not going to be moles per dm cubed because we've got partial pressure, and the units for partial pressure are atmospheres. Yeah, so you could also be using pascals. We just happen to be using atmospheres. Ahmed, it would be nice, wouldn't it, if you could just do one question like this and then get the whole paper. Yeah, so this is why we practice. This is why I'm here. This is why we're having a go at questions like this. But yeah, so just remember that pressure is either measured in pascals, kilopascals, or atmospheres. And the way you work out your units is you shove it in the equation just like you would for KC. And if you can see here, both of these two terms are going to cancel. So it's going to be 1 over atmospheres. So we've got ATM to the power of -1. So we're not in kilopascals, people, because we were given it in atmospheres. So just make sure you check what you were given your partial pressures in. If it's in atmospheres, use atmospheres. If it's in pascals, use pascals. If it's in kilopascals, use kilopascals. So be careful. I'm going to move forwards. So this is essentially the same. It's going to be very similar to what we talked about with homogeneous and heterogeneous KC. It's the same concept. So tell me, when all the products and all the reactions are in the same state or phase, what is that? Is that homogeneous or heterogeneous? So you kept everything in fractions and got 1.69 at the end. That's all right, Fatima. In the exam paper, it will have like a range if it's that specific. So I think that you're probably all right. So Logan, not quite homogeneous. Remember, homo means same, hetero means different. So yeah, so the first one is homogeneous. So the second one has got to be heterogeneous, right? I cannot approve of shots because I don't know if you're over age or not, and I am on YouTube, which means that I don't want to get parents complaining that I have encouraged a drinking game. So please don't do that if you are underage. Only 18s and over should be consuming things. Okay, so if it's heterogeneous, tell me, what do you think that Kp is going to be the normal equation, different equation? What do you think happens to Kp? What happened to it with Kc? Anyone? Does anyone remember? Kp is homo. Okay, a tetanus one, a tetanus shot. Also, don't do that, Aluna. I think that you shouldn't have more than one tetanus shot. Only products, same for homogeneous. If it's in excess, you don't include it. That is what I was going for. Thank you, Fatima. So if something is in excess, which means there's like so much of it that its pressure or concentration changes don't affect the equilibrium, then we do not include it in the equilibrium equation. And what do you think in this here, if this is an equilibrium reaction, what states in this do you think are in such high pressure that we don't include them? So is it going to be gas or is it going to be solid? Because that's the only thing that's in there. What is in excess over here? Solids, yeah. Solids are avoided. We do not include solids in our, I mean, like, I think it's a little bit more intuitive with pressure, right? Think about just how much pressure it is in a solid if all the particles are right next to each other. There's not any point measuring the pressure. It's massive compared to the CO2's pressure. So changing the pressure is not going to make any difference. So we don't include it. So Kp in this case is just the partial pressure of CO2. And then for homogeneous, we do it exactly the same way as we've been taught. So essentially everything you've learned up to this date has been homogeneous. So everything you've learned applies perfectly nicely to homogeneous equilibriums. If it's heterogeneous, you need to get rid of the things that are in excess in the equation, and that's for concentration and pressure. And I'm going to leave it at that because I think I've explained it. If somebody's still confused, you can ask me at the end. But yes, so don't include your solids, please. How are we feeling? We're almost at the end. We've got one more exam question or two or something, and then we're done. So how are we feeling, lovely people? Happy? Aaron is happy. I'm glad you are happy. Logan is happy. Oh, so much happiness. Yay, Tracy's happy. Aisha's happy. Fatima's happy. Oh, good. Deck is happy also. word. That is not fair. That's not an expression. Can't give me no expression. Night Hardcore, interesting name. I'm in year 12. Would this live stream be helpful? You're jumping the gun a little bit. Night Hardcore. In fact, it's a very apt name for this situation, right? So you kind of need the knowledge of equilibrium from year 12 for this to make total sense, even though I try to sort of like catch everybody up at the beginning just in case they didn't get it last year. So you can watch it and you can do it, but it will make more sense next year. It's totally up to you. It depends how you learn best. It's useful, but it's not going to be as useful as if you had the prerequisite knowledge. Aisha, stop trying to get people to confuse me. That's not very nice, is it? Something about kindness. I'm sure there's a saying somewhere that I could bring in here. I'm going to move on instead of being sort of like hazed by my YouTube students. Okay, exam question. So ethanoic acid can be manufactured by the following reaction, which is carried out between 150 degrees and 200 degrees. And we've got some methanol, we've got some carbon monoxide, and we're making ethanoic acid. So a mixture of 50 moles of methanol and 50 moles of carbon monoxide reaches equilibrium at pressure at 32 atmospheres. So please note we're in atmospheres, not pascals or kilopascals. At 175 degrees, the equilibrium partial pressure of ethanoic acid is 22 atmospheres. Write the expression for the equilibrium constant in terms of Kp for this reaction. So this one is you just have to remember which way around to put it. Reactants on top or products on top? Tell me what goes on top, reactants or products? Oh, thank you, Fatima. Beautiful. Kp is equal to P CH3CO. So that's our little ethanoic acid, P, and then we've got our methanol, and then CO. Yeah, so thank you, Tracy. Thank you, Decca. Products on the top. Right. So the next question says, calculate the partial pressures of methanol and carbon monoxide at equilibrium. Okay, so this is another one of those sort of like we're taking things away type things. So what is the pressure? What is the carbon monoxide pressure at equilibrium? This is me just getting you to like read the question because that's important and people actually don't do that very often. So what is our partial pressure for carbon monoxide? Do we need to add P in a bracket? So I probably should have put either like a dot here or a times here or put them in brackets. So I'm going to put a dot in. That makes more sense. Yeah. Thank you, Logan. Thank you, Aisha. We've got 32 atmospheres for carbon monoxide. So what are we going to do with that? How will we figure out the partial pressures of methanol and carbon monoxide at equilibrium? What do we need to do with this? Because this is the only equilibrium. Whoops. This is the only equilibrium pressure that we have. So Fatima says 22 times 32. Not quite. We don't want to go backwards. Daka says 50 minus 32. Where did you get 50 from? Oh, 50 moles. Okay, so we have to keep, we're looking at pressures only. What's the only other pressure we have, guys? Fatima's kind of already maybe put that in there. What's the only other pressure we have? Yeah, 22.2. Okay, so what we have here is we have the equilibrium pressure of carbon monoxide, which is over here on the side of reactants, which is 32. And then we've got the partial pressure at equilibrium for ethanoic acid, which is our product. So the way that we're going to, is that at equilibrium? 50 moles at a pressure of, okay, sorry. How did I get 32? It says it here. Aaron, it's in the question. It's right here. So at 175 degrees. Okay, so we've got 32 as the partial pressure of carbon monoxide when it reaches equilibrium. And what I'm going to do is I'm going to take away the partial pressure of ethanoic acid, because that's not going, because that's in our products. So what that's going to give us is what the partial pressure left over at 175 degrees is. So we've got 32 atm at the beginning, and then once it reaches 175 degrees, we've got a partial pressure of ethanoic acid of 22.2. So I'm going to take them away, which gives me 9.8. And so we know that at equilibrium, this one here is 22.2 atm, and both of these are 9.8 together. So if they're 9.8 together, how do we work out what they are separately? Divide by 2. Yeah, thank you, Logan. Thank you, RN. We want to divide it by 2, which gives us 4.9. And we know that we divide by 2 because they're both in the same mole fraction, right? They both have 1 mole of each. So our partial pressure of methanol is 4.9, and our partial pressure of carbon monoxide is 4.9 also. Yeah, well, you're also right, divide by 2. Okay, so the next bit is calculate the value of Kp for this reaction at 175 degrees. Include the units in your answers, give your answers to 3 significant figures. So please, people, I'm not going to remind you at the end. When I ask you for the answer, if it's not in 3 significant figures, you're a crazy person, because you will lose your marks for not putting it to that. Is this only possible because we both start off with 50 mole? Yeah, so essentially because the mole fractions are the same, the amount's the same, we know that the mole, we know what the mole fraction is, so we can just divide by 2. Cool. So we already know what our formula for Kp is, and we have our partial pressures, so I'm just going to shove them in. So we've got 22.2 for our ethanoic acid. We've got 4.9 for each of those because we've just worked that out. So does somebody want to shove that in their calculator and tell me what it is? Beautiful. So Logan said it, but I'm going to... Is that 3 significant figures? Yes, it is. 3 significant figures means that you've got 3 values that aren't 0, essentially. So it counts, 0 counts if it's in the middle of things, but if it's like right at the beginning or right at the end, it doesn't count. So yeah, we're right. So it's 0.25. So we also want units. So what I'm going to do is remind you guys that, somebody actually, you guys work out the units. Show me how you work out the units. I'm not going to do anything. I'm going to drink tea. Yep. Yeah. So show me how did you do that? How did we get atmospheres to the -1? We're not in Pascal's, Aisha. We've got to be, remember, it says it here, atmospheres. We're in atmospheres. Yeah. So it's not just atmospheres, it's atmospheres to the -1. And I'm going to go through that really quickly. Yes. Oh, thank you, Fatima. Perfect. So we've got atmospheres for the top, and then it's over atmospheres times atmospheres, which means that 2 of them cancel, which means that we just have 1 over atmospheres, and 1 over something we can write as to the power of -1. And you guys have done so well because we're done. Oh, and I'm running late, but you know, whatever happens every time. I will learn to cut things down, but you've done super well, which means I'm going to do all the housekeeping, and then you guys get your discount, and then you get to ask me questions. So we did equilibrium in terms of concentration. We did homogeneous and heterogeneous equilibrium for both concentration and pressure. And then we looked at pressure equilibrium constants and partial pressure and mole fractions and all that jazz. And you should be able to do calculations with it in future. So this whole thing is to show you guys what SnapRevise 2.0 is going to be. And it's coming out really, really soon, October the 16th. And essentially, we've just got this really cool system that's supposed to be like really smart learning. So like you'll watch videos and answer questions, and then we'll show you what you don't know and what you do know and give you exam questions for the right things instead of you repeating yourself loads. It's just really cool. I wish it was around when I was doing my A-levels, but it wasn't. I just had textbooks and confusion. So all of the web classes and sort of like the ability to like send me questions and be like, I'm confused, help, will be in our ultimate package. If you already have SnapRevise, you'll automatically get the basic package. It's cheaper if you buy it now and then later on upgrade, although you're welcome to wait till October the 16th and pay more. But we do get that not everybody can afford to buy stuff. Students tend to be the skint members of the population, so we'll still have some free web classes for those people. Yes, cool. Set reminders for the web classes. If you are forgetful, go to SnapRevise on YouTube. And if you go on our live stream thing on the homepage, then you can set reminders for everything. The next year 13 one is on next Thursday, and it's going to be acids and bases. And if you're in year 12, because you've like jumped the gun, that one's on next Tuesday. And I don't remember what that one is. Yes, I do. It's reacting masses. So also if you want to revise reacting masses, so that's like your moles, concentration, volume stuff, you should come on Tuesday as well. I know that lots of people find that quite difficult, so I would advise coming to revise that. Are there going to be any for physics? Yes, eventually. Right now, we're just sort of like, because it's new for us to do web classes, we're just trialing chemistry and biology for now, and it's going quite well, so we will have physics for you soon as well. Yes, that's the so the ultimate package is going to have live classes. Aaron, when am I doing period 3 properties? So that one's a tricky one because it's only in one of the exam boards. So possibly we won't be doing it, but I have had some requests. So I'm going to think about the best way to do that, but it's only one of the exam boards. So it's a bit tricky. Yes, Tracy, there will be maths at some point. But again, we just decided to start off with chemistry and biology because they were most in demand and see how it went. And then now it's good. So we'll add in physics and maths. And here is your lovely code. See, my words are gone. It's a code. Look, EQ40. You can get cheap courses. So when October 16th happens, you'll be upgraded. But the things you'll have access to now are what SnapRevise is currently. Are there any for C3 and C4? That's all coming. So if you mean web classes, that's coming. Ha! We made it to the end. Do you have questions for me? And this time I will not, leave, but you do have to ask them now. So do you have questions? And it has to be related to this topic. It can't, or just like A-levels in general, but it can't be a random other topic. And also, if you guys could appreciate the majesty of the questioning pineapple, I would appreciate that because I really like the pineapple. Any questions? I'm gonna give it like 60 seconds for you to say yes, I have a question, and then I'm gonna head and try and find some not gross biscuits, or actually just have dinner. Eating is a wonderful, wonderful thing. Not getting any questions. Okay, all right. I'm going to take that to mean that I explained everything so fabulously that you couldn't possibly need questions. Thank you. I'm glad you appreciate it. Abyaz and Aaron, you're welcome. Have a lovely evening, and I will see you on Tuesday or Thursday, whichever you come to. Welcome, Logan. Dum, 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 dum.